Hi everyone, hello and welcome. This video covers our section 1.4 and section 1.5 from class today. So, all right, here we're talking about functions and change, and then direct proportionality. So first the functions. Well, we introduced what functions were, we started working with them. Now we're going to see how we can use functions to identify how there might be changes in underlying relationships that we're modeling using the function. So for instance, suppose we want to be able to compare the growth in the population of some growth in termite population over time. So here's an example. We have population as a function of time of a colony of termites, t months after it started. So we have months, t, 0, month 4, month 8, month 12. And then we have the population, 1200, 2400, 4800, and 1600. Okay. So if we're looking at the rate of growth, one thing we can do is just study what happens in terms of the absolute population change. So if we're thinking from the initial starting point to 4 months later, or the initial starting point to 8 months later, we see we grow from 1200 to 2400, or we double in that time. Population's doubled. It's grown by 1200. And then what about the span from 0 to 8? Well, here it's easy to see if we subtract the population in time 0 from the population in time 8, the growth was 3600. And so we see, oh, well, in the first 8 months we grew 3600 termites. In the first 4 months we grew 1200 termites. So we have 3 times the growth rate in the first 8 months as in the first 4 months. And also there was twice the time to grow, because here we only had 4 months, here we had 8 months. And what this tells us is that we had a big jump right here. Okay. So the next thing we can do is say, well, suppose we're not interested just in the absolute growth of the population, but we're interested in the rate of change. So in particular, we can calculate the average rate of change. The average rate of change in the first 8 months, it's the change in population divided by the change in time, right? So delta p, this delta just means change, and this is change in t. So we have delta here. The change in population, 4800 minus 1200, that was 3600 divided by 8, because our change in time was 8 months. So we have 450 termites per month is the growth rate, the average growth rate. And then the average rate of change in the first 4 months, well, this is our change in population from month 4 to month 0. And then over those 4 months, we find, oh, 1200 divided by 4 is 300. So we have a growth rate, average growth rate of 300 termites per month. And this slide just summarizes that result. And then here, this is just so we can compare these things. We can see, oh, the total population change differed by a factor of 3, right? We grew 1200 termites from month 0 to month 4, and we grew 3600 termites from month 0 to month 8. And over that same period, the average rate of changes differ by only a factor of 1.5, right? 1.5 times 300 is 450. All right. All right. More generally, here's how we can talk about average rate of change. So here's an expression for the average rate of change. Suppose we have some input for the function y equals f of x, which is changing from x equals a to x equals b. Then we'd have our change in input. It's just our new x minus our old x, so b minus a. And our change in output, our new y minus our old y, so f of b minus f of a. And the average rate of change is going to be the change in output over the change in input. So delta y over delta x, or f of b minus f of a divided by b minus a. And just looking back here, that's exactly what we had. This is like f of b minus f of a, and this is b minus a. Right. So here's some more numerical examples. Suppose we had an actual function rather than a table. Suppose our function is g of x. This is the quantity x minus 1 squared plus 5. And we're interested in the change on the interval 0 to 4 and the change on the interval minus 3 and 1. Well, on the interval 0 to 4, g of 0 is just 0 minus 1 squared, so that's minus 1 squared is 1 plus 5 is 6, and g of 4, plug in 4 for x, 4 minus 1 is 3, squared is 9, plus 5 is 14. So g of 4 minus g of 0 is 16 minus, or is 14 minus 6, and our change in x value was just 4 minus 0. So we have 8 divided by 4 is 2. What about that other interval? Well, now we're interested in g of minus 3 and g of 1. G of minus 3, we have minus 3 minus 1 squared is 4. 4 squared is 16, plus 5 is 21. And 1 minus 1 is 0, squared is 0, plus 5 is 5. So we have g of 1 minus g of 3. So we have, let's see, so I should have written this as 5 minus 21. So we should have negative 16 divided by positive 4. So this should be minus 4, right? So I'll change that for the slides on Canvas. But what's the problem? Well, this would be like our f of b, and this is our f of a. This is our b. This is our a. What did I do here? Well, this would be like f of a. So I reverse these. This should be 5 minus 21 divided by 4. So it should be minus 16 over 4 or minus 4. All right, sorry about that. All right, so for the termite colony from before, what's the change in population from over the last 8 months or for months 4 to 8? So we're interested in the change between month 4 and month 12, and we're comparing that to the change from month 4 to month 8. So going from 2400 to 4800 and going from 2400 to 1600. And then we're interested in the average rate of change over that period. So the change in the last 8 months, this is just f of 12. Well, f of 12 is 1600 minus f of 4. Well, f of 4 is 2400, so 16 minus 2400 is minus 800 termites. We lost 800 termites when we go from month 4 to month 12. Now, of course, that's omitting some interesting information, which is that before we lost those 800, we also went up quite a bit to our maximal population over this interval. But that's not what this is interested in. This is just interested in the absolute change from this point in time to this point in time, right? All right, and the change from month 4 to month 8 was a gain of 2,400 termites, right? 2,400 plus 2,400 is 4,800. So the negative sign in the last 4 months indicates the population decreased, but the positive sign on the other result tells us for the first 4 months of the interval it increased. I should actually say the negative sign on the change for the last 8 months, right? Because that was going from here to here. Okay. So here's the average rate of change in the last 8 months. Basically, it's the calculation from before, 1600 minus 2400 divided by 8, or minus 100 termites per month. The average change from months 4 to month 8, that's 4,800 minus 2,400 divided by 4, or 600 termites per month. What's going on here? Well, you'll notice this is exactly the same work as before. This is my numerator. This is another numerator, right? What's my denominator? It's the time period. It's 12 minus 4 is 8, and it's 8 minus 4 is 4. Okay, the average rate of change over the last 4 months is negative because the net change is negative. I should say last 8 months again, because that's what this was. This is the last 8 months. So sorry about that. Okay, so another thing we can do is we can reflect on the algebraic structure, and that can help us solve these problems. So for instance, here's a car driving example. Suppose the car is driven f of t miles in t hours after it begins. F of 4 is the interpretation. It's the distance it's traveled in 4 hours of driving. F of 24, that's the distance traveled in a day's worth of driving if you do nothing but drive. What's the change in the distance over that time? Well, it would be whatever is your f of 24 minus whatever is your f of 4. I'm just going to say hypothetically, it's f of 24 was 1,400, f of 4 was 200, then 1,200 would be the amount we've driven in those 20 hours. What would be the average rate of change? Well, this would be our output in f of 24, our output in f of, I should have had f of 4 here. That's another typo there. And then 24 minus 4, what's that? This is just the difference in our inputs, right? This is like f of b minus f of a, b minus a. So we have 1,200 divided by 20, or average rate of change is 60 miles per hour. Why do I know it's miles per hour? Well, this right here, this is measured in miles. This is distance in miles, and then that's the numerator, and the denominator is time, measured in hours. So this is 60 miles per hour. Right, so once again, the expression f of 24 minus 4 is a difference, and it's measured in miles. The statement f of 24 minus 4 equals 1,200 tells us simply the car goes 1,200 miles between hour 4 and hour 24 of the trip. And in this expression, it's a fraction. The numerator is in miles, denominator is in hours, so the fraction is miles per hour. So, like I was saying before, this statement f of 24 minus f of 4 over 24 minus 4 equals 60 tells us the average speed of the car during the 24-hour period is 60 miles per hour. Okay, so that just summarizes everything I said previously. So here's an example. Using this idea, suppose the car traveled f of t miles t hours after it begins. Interpret the statements in terms of the journey of the car, including its units, so including its miles per hour, whatever, or miles. Okay, f of a plus 6 minus f of a equals 240, and f of a plus 6 minus f of a divided by 6 equals 40. So interpret these statements in terms of this example. Stop the video and do this. Okay, so what does f of a plus 6 mean? F of a plus 6 would be, if we start at time f of a plus 6 is 6 hours hence, 6 hours later. So this is giving us the distance we've traveled in a 6-hour period. So this is the distance in 6 hours divided by those 6 hours is going to be our miles per hour. So, okay, let's go over this more carefully. F of a is the distance the car travels after 8 hours. F of a plus 6 is the distance after 8 plus 6 hours, or after 6 more hours. Therefore, f of a plus 6 minus f of a equals 240 just means the car travels 240 miles between the 8th and 8th plus 6 hours after starting. And then we'll divide this by the 6 hours that we've driven, and that tells us that the denominator, this is the total time of the trip. The numerator is the distance over the 6 hours, so the ratio gives us the average rate of change of f, or the average speed of the car, which is 40 miles per hour. Just a couple comments. It can be helpful to consider the units of the measurement of the input and output quantities because it assists our interpretation of our problem. If the input's measured in hours, output is the distance traveled in miles, then the average rate of change of the function is just miles per hour. If the input is time measured in months and the output is the number of termites in our colony, well, then the average rate of change is just measured in termites per month. And these are the two examples that we saw. Okay, so here's another example, a ball example. So a ball is thrown in the air and has a height of h of t is equal to 90t minus 16t squared, feet after t seconds. What are the units of measurement for the average rate of change of h? What does your answer tell you about how to interpret the rate of change in this case? Find the average rate of change of h between t of 0 and t of 2, t of 1, t of 2, and t of 2, and t of 4. And then use the graph of h to interpret your answers above in terms of the motion of the ball. So just interpret the expression. The ball thrown in the air has height h of t is 90t minus 16t squared, feet after t seconds. In the expression, well, the numerator is in feet, the denominator is in seconds. So this is going to give us feet per second. Feet per second is a velocity. Right? All right, so a ball thrown in the air has the height given by this function. Let's find the average change in height between the initial period and 2 seconds later. So we take h of 2 minus h of 0 divided by 2 minus 0. We just evaluate this function at a value of 2, so 90 times 2 is 180, minus 16 times t squared is 4, so 16 times 4, minus 0, 0, y, well, you plug in 0 here, you get 0, 0 minus 0. And this calculates out to 58 feet per second. How about this interval between t1 and t2? Here we just evaluate the function at 2. Then we evaluate the function at 1, and we take their difference. We already calculated this one before. This next one, h of 1, that's 90 minus 16. Turns out this is 42 over 1 feet per second. And this last one, now we evaluate the function at 4, we evaluate the function at 2, and here we have minus 6 feet per second. And here's the picture. The graph shows the ball's height rising to a peak between T2 and T3, rising to a peak between T2 and T3. Average velocity is positive during the first 2 seconds and height is increasing. Height is also increasing between T is 1 and T2, but since the ball rises more slowly, the velocity is smaller. Here's sort of tapering off. Between T2 and T4, the ball rises and falls, experiencing a net loss in height, so the average velocity is negative. It's going up, it slows down to a stop, reaches a peak, stops momentarily, and then accelerates at a rate of 9.8 meters per second squared, or 32 feet per second squared. Okay, so the next thing we'll think about is section 1.5. Think about a real-world situation, and in these cases, oftentimes we don't have a function. We have to build one ourselves. This is what economists do. Very often, the problem we want to solve doesn't come with an off-the-shelf equation, although we have some models we can reach for, and then we have to tweak them to fit the particular circumstance. And we have to use our judgment to make sure we've done this appropriately. It's kind of those skills that we're going to be building in section 1.5. So. First, a definition: direct proportionality. A quantity Q is directly proportional to the quantity Q, or T, if Q equals K times T, where K is the constant of proportionality. Basically, what this is saying is that we've got a relationship that's relationship reflecting direct proportionality if we can represent this relationship with this linear equation. Usually, we just say Q is proportional to T. So an example would be sales tax. Suppose sales tax in Tucson, Arizona is 8.6%. Then tax T on a purchase of price P is a function given below. So tax is 8.6% times price, or T is equal to 0.086p. And tax is proportional to the purchase price. If the price doubles, so does the tax. And then the ratio T of P is a constant. It has to be, right? Solve this thing or divide this thing through by P, you'll get T of P. It's equal to the constant of proportionality. It's equal to the tax, right? The tax percentage. Not the tax, is equal to the tax percentage. All right. Here's another example. If my car gets 30 miles per gallon, how far can I travel on 1 gallon, or on 2 gallons, or on 10 gallons, or on 20 gallons? We can express the distance d in miles traveled as a function of the number of gallons g used. And then we want to explain why d is proportional to g with a constant proportionality of 30. So do this, stop the video, and do these examples. All right, so we can resume. If the car goes 30 miles for every 1 gallon, then the distance for 1 gallon is 30 miles. If it goes 30 miles for every 1 gallon, then for 2 gallons, that'll let me go 60 miles. 10 gallons allows me to go 300 miles. 20 gallons allows me to go 600 miles. And then just note, when the number of gallons doubles from 1 to 2, the distance I can travel doubles from 30 to 60. When the gallons doubles from 10 to 20, the distance I can travel doubles from 300 to 600. And that should be pretty intuitive. If not, then stop and think about why that's got to be the case and how that relates to what we were saying here about the proportionality and the sales tax. Okay. Lastly, an additional gallon allows me to go another 30 miles. So we can say the distance is equal to 30 times g. D is proportional to g with a constant of proportionality of 30. That's just the car's gas mileage. Here's something about the behavior of proportional quantities. If Q equals KT, then doubling the value of T doubles the value of Q. Tripling the value of T triples the value of Q. Halving the value of T halves the value of Q, and so on. Okay, that's just true in general. Here's an example. Suppose we have Emily and Jack. Emily pays 5 times as much for a car as Jack. Jack pays $200 sales tax. How much tax does Emily pay, assuming they have the same tax rate? Well, Emily's car cost 5 times as much as Jack's, so Emily's sales tax is 5 times as large as Jack's. Emily pays 5 times $200 or $1,000 in sales tax. What does Jack pay? Stop the video. Oh, just kidding. I told you Jack pays $200. Okay, going back to my car, 30 miles per hour. How many gallons of gas are needed for a trip of 5 miles, 10 miles, 100 miles, 290 miles? So 290 miles is the distance that I'm well familiar with. All right, so find G, the number of gallons needed as a function of D, the number of miles traveled. Explain why G is proportional to D and how the constant of proportionality here relates to the constant from my earlier example. That was just a couple slides ago. Okay, well, if the car gets 30 miles per gallon, the amount of gas needed to drive m miles is just m divided by 30 of a gallon. So the gallon for 5 miles is let's see, 5 divided by 30. So this should be 5 rather than a 6. Should be miles is 5, so this should be 5 divided by 30, or 0.2 gallons. The gallon for 10 miles is 10 divided by 30, or 0.33 gallons. To drive 100 miles, we need 100 divided by 30, or 3.33 gallons. And to drive 290 miles, I need 290 divided by 30, or 9.66 gallons. So this isn't actually my gas mileage, because to go 290 miles, I need 11.5 gallons. So you can figure out what my actual gas mileage is. Since each mile takes 1/30th of a gallon of gas, we have G is equal to D over 30, or 1 over 30 times D is equal to G. So G is proportional to D, and the constant of proportionality is 1 over 30. So G, this is our 1 over 30 is like our K, and then our other variable is D. And this is actually the reciprocal of the constant from the earlier example, which is just 30. We see gas is proportional to D by solving. D equals 30G. What's going on? Well, look, we have two equations. This one is G as a function of D. This one is D as a function of G. Right? It's the same relationship. It's just that one version is sometimes better for thinking of some applications, and the other version is better for thinking of other applications. Okay, so here's a series of exercises. Do these functions represent a direct proportionality? If so, find the constant of proportionality K. And here's my hint. Oftentimes, we actually have to rewrite the expression of the function to see if it fits to represent direct proportionality. So f of x equals 17x. G of x equals x over 37, g of a equals 3a plus 7a, v of t equals square root of 3 times t, a of b equals b times pi squared, q of t equals 3 plus 4t. Okay, so pause the video and then see if you can do these on your own. Note, this is not the area of a circle, is it? The area of a circle is pi r squared. This is b pi squared. Okay, the first one, f of x is proportional to x, constant of proportionality is 17. The second one, g of x is proportional to x with k is equal to 1 over 37. Here we have to simplify. Let's collect like terms. So the constant of proportionality is 10. This one's also proportional to t with a constant k equals square root of v. Notice this square root only goes to the number, so this whole thing is a constant. It doesn't go to the variable. If this is square root of t, we might think about this differently, right? Here, the constant of proportionality, k, is just pi squared. And then what about this last one? Oh, actually, no. Q of t is not proportional to t because of the constant 3 on the right-hand side that's being added in, right? Our definition of proportionality was that we had to have the output is equal to some constant times the input. And we have that up here, but we don't have this down here because we have this addition with this 3 constant. So comment, solving for the constant of proportionality. If we don't know the constant of proportionality, we can find it using one pair of known values for quantities that are proportional. So here's an example. For my summer job at the amusement park, I earned $81 for 9 hours of work. Express my earnings as a function of the number of hours worked. What's the constant of proportionality and the practical interpretation? So stop the video and do this. Here's my sort of editorial comment. I would have been way better off spending those summers learning something valuable like computer programming or some skill that would be useful to me today, because that's something I'd like to do with my time now. But the value of my time, my opportunity cost in terms of what I give up to be able to learn something new is much higher than it was back then. So, and the value that I got for the summer, I'd earn between $2,000 and $4,000 for a summer, it wasn't worth it, right? All right, so for my summer job at the amusement park, I earned $81 for 9 hours of work. So we have earnings is equal to f of t equals k times t. E is the earnings, t is the hours worked. We already have 81 equals f of t, or f of 9 equals k times 9. Solving for the constant of proportionality, we have k is equal to $81 divided by 9 hours, or $9 per hour is the rate. So k equals $9 per hour, that's the hourly wage. And you might have been able to recognize that from the problem without even doing this calculation. Why do we do the calculation? It's so that we can see how the theory gets applied here in this example, so that it helps us when we need to apply it later to a different example. So another example, physicians know a person's heart mass is proportional to body mass. Suppose we have a person with a body mass of 90 kilograms and a heart mass of 0.54 kilograms. Find the constant of proportionality. And then using that constant of proportionality, let's estimate the heart mass of a person with a body mass of 70 kilograms. So stop the video, go ahead and give that a try. Now returning, a person with body mass of 90 kilograms has a heart mass of 0.454 kilograms. Find the constant of proportionality. Well, with h as the heart mass in kilograms and b as the body mass in kilograms, we have for some constant k, which we're going to find, h equals k times b. So we substitute in, b is 90, h is 0.54, solve for k, 0.54 divided by 90, our constant of proportionality is 0.006. Well, let's just use this formula, right? Now let's plug in our 0.006 here, multiply by our body mass of 70, and that gives us a heart mass 0.42, right? So that solves our last part. Estimate the heart mass of a person with body mass of 70. Okay. Comment about proportionality and rates. So the average rate of change of a function depends on the interval over which it's computed. Let's explore the average rate of change of a proportional relationship over different intervals. So the amount of money I earned, this should be a the, clearly, sorry for the typo. E dollars after working t hours was E equals f of t of 9 times t. What's the average rate of change of the money earned between 10 and 20 hours and between 6 and 8 hours? Compare the answers above to the constant of proportionality. Use the algebraic structure for the function to explain why this happens. All right, so pause the video, find the average rate of change between these two intervals. Remember how you do that? We have what? F of b minus f of a, and then b minus a. Okay, so we have 180 minus 90 divided by 10, or $9 per hour. And then we have 64 minus 48 over 2 is $9 per hour. How do I know that? Well, earnings is 9 times t, so 9 times 10 is 90, 9 times 20 is 180, 9 times 6 is, let's see, 6 and 9, 9 times 6 is 54, and then what am I supposed to have here? Oops, not 48, right? So I want 9 times 8, I want 72 there. Well, anyway, so I'll fix that for Canvas. The average rate of change is the same for both intervals, and it's equal to the constant of proportionality, k equals 9. So since the formula for f of t is 9t, every time t is increased by 1, I earn $9 more. So my earnings are changing at an average rate of $9 per hour. And last thing we'll talk about is a family of functions. So the functions y equals f of t equals kt all have the same algebraic form. We can think of them as a family of functions. It's all linear functions without an intercept. These are linear functions going through the origin, right? Right? There's no intercept. Think about y equals mx plus b form. This is like m, this is like x. Okay, we can see this graphically. Their graphs are all lines, and they all pass through the origin. There's differences between the functions. These correspond to different values of k, to different slopes, right? K is a constant for any given member of the family, but changes from one member to the next. K is a parameter for the family. You can think of what this is going to look like, what the graphs are going to look like. It's going to be straight lines, just with different slopes. So it looks something like this. So here's one. If k is equal to 3, we have this dark blue line, which has a slope of 3. If k is equal to 1, we have the line y equals t. This is the 45-degree line right here. Suppose k is equal to 1/3. Well, then we have this green line. Y equals 1/3 t. Suppose k is equal to -1. Then we have this red one with a negative slope. And as you might guess, there's infinitely many lines, right? So this is actually this could actually be incredibly dense with lines. I just picked 4 to look at. And they're all part of the same family of functions. For a given k, we get a different line, but all have the same underlying structure. Okay, so very good. Let me know if you have questions.